Hi, my name is Pravesh Shrestha and this is my video submission for assignment 2 of Com 3132, and in this video I'll walk through my completed notebook step by step, explain each line of code and the answer the required questions about neural networks and overfitting. So for the first part, what I did was I have imported the pandas, the necessary libraries. Pandas is used to read and work with our CSV file as data frame. NumPy is imported for numerical operations. Train test split from skset learned lessons divide our data into training and testing portions. Two categorical from Keras converts integer labels into one hot encoded vectors, and Keras and layers from TensorFlow are used to build our neural network. I also set path here. I use the actual file name, the assignment to iris, to point directly to the CSV file I have uploaded in the Colab given in our assignment. And for section for the question number 1, we can see that we have shown the first 5 rows on the data frame right here. So now we are going to the 1b. Here I use the pd.read csv to load the csv file into variable called iris. Then I call the iris.head to display the first 5 rows here in the data frame. As you can see on the screen, the dataset has 5 columns: sepal length, sepal width, petal length, petal width, and species. The species column currently contains string values. We need to convert those numbers before feeding them into the neural network. The dotmax function to replace each string with an integer. So Setosa becomes 0, versicolor becomes 1, and versinica becomes 2. When I call the iris.head, again you can now see that species column is like 0 0 0 0, all special, the all Setosa's rows now as integer. We can see it's right here. Now all the Setosas here are integer. Like this is necessary because our model only works with the numbers. So going to the another question, I have split the data frame into features and labels. X is assigned using the iloc, which selects all the rows and the first 4 columns, the measurement feature. And for 3b, y is assigned using the iloc, the -1, which selects the last column, the species label that we want to predict. And going to the question 4, for I use the train test split here. The train test split x and y to I set test size to 0.2. So 20% of the data, which is 30 rows, goes to testing, and remaining 80, which is 120 rows, goes to training. I also set random state 1 2 3, so that everyone in the class gets the same shuffle when splitting the data. You can see that the head of x train at the row 130, x train at the row of 130, 119, 29, these are shuffled randomly. And when I check the length of you can see the train head, and when I check the one second, when I check the length of x train, it gives me 120, and length x test gives 30, exactly what we wanted. it gives me length 120, length 30. This is what exactly what we want. For the question number 5a, before training, I converted the integer labels into one on hot encoded format using two categorical. Now what does it turns into 0 into 100, 1 into 010, 2 into 001, and we need this because our final layers uses softmax activation and categorical cross entropy loss, both which requires one hot encoded labels. You can see the softmax here and the layers. Of course, so now starting the model 1 for the question number 6. So what I'm doing is I'm building the first sequential model. It has 3 dense layer. So the first hidden layer has 100 neurons with the ReLU activation. The second hidden layer also has 100 neurons with ReLU activation. The output layer has 3 neurons, one per class with softmax activation. Softmax produces probability for each class, and the class with the highest probability is the prediction. I compiled the model with RMS prop as the optimizer with adjust learning, and also the categorical cross entropy as the loss function. The standard choice when labels are one hot encoded, and accuracy as the metric monitor. You can see the screen that for 20 epochs the 12 epochs run on the 20. The accuracy improved progressively starting from around 58 to 95, climbing up through the epochs as the model learned the patterns. You can see the test. So after training, I evaluate the model on the test set. The result shows that the loss approximity is 0.138 and the text accuracy is 10. This is the excellent result. The model correctly classified 29 out of 30 test samples. So for the question 9a, for we're creating a model 2, I kept the same structure but reduced the hidden units from 100 down to just 10 neurons per layer. We can see it here. And reduced training from 20 epochs down to only 4 epochs. Looking the training output, the accuracy during the training only reached like 50 percent, which shows the model was still learning and hadn't converged yet. When I evaluate the test accuracy, it came out at 30%, essentially not the 50%, essentially random guessing for a 3-class problem. This directly shows that the impact of fewer neurons and fewer training epochs. The model simply didn't have enough capacity. For enough time to learn meaningful patterns. For section 10a, I will be explaining each. So let's go to the question number 1. How the number of layers or hidden units could impact the accuracy of our model. So how does so more neurons give the model more capacity to learn complex patterns. Model 1 with 100 neurons per layer achieved 95% accuracy, while model 2 with only 10 neurons achieved only 50% accuracy. That massive difference just from reducing neuron count. More layer also help. They allow the model to learn hierarchical features. However, adding too many layers or neurons can lead to overfitting, where the model memorizes training data but fails on new data. So we always need to find right balance. For the next question, do we always suffer from overfitting? So the answer is no, we don't always suffer from overfitting. In fact, with a simple and clean dataset like iris, overfitting is less concerned. Model 2 actually suffered from the opposite problem, underfitting, where the model was too simple and didn't even learn the training data well. Overfitting only becomes a real concern when the model is too complex for the model of data available. For example, using 100 neurons on a dataset with very few training samples, with the iris dataset being well balanced and clean, Model 1 generated it generalized well to the test set. For the question 3, how we detect overfitting? We can detect overfitting by monitoring both training accuracy and validation accuracy at the same time across epochs. If training accuracy keeps increasing but validation accuracy starts decrease or the plateau, that is clear sign of overfitting. The model is memorizing the training dataset instead of learning generalizable patterns. In Keras, we can pass validation data test into the fit method to track both losses side by side during training. A large and growing gap between the training loss and validation loss confirms the overfitting. And how can we reduce the overfitting? So there are several ways to reduce the overfitting. The first one is dropout. It randomly disables the neuron during training so the model doesn't over rely on the specific connection. The second one is reducing model complexity using the fewer layers of neurons, just like we saw going from model 1 to model 2. Early stopping, automatically stopping training when the validation loss stops improving. And the fourth one is more training data. If you give like more diverse examples, help the model generalize better. And the fifth one is L1 or L2 regularization, adding a penalty to large weight values to prevent the model from becoming too confident or training data. For 10b, in this section, the 10b, I changed one parameter at a time from Model 2's baseline settings of the Aramus prop optimizer. 10 neurons, 2 hidden layers, 4 epochs, batch size 10. So we can see that we changed the optimizer to Atom. So the Model 3 output, the test accuracy 20%. The Atom is another popular optimizer that uses adaptive learning rates. And this run with only 4 epochs and 10 neurons, it actually performs worse. 20%, the test accuracy is like 40%. This shows the optimizer alone cannot compensate for the insufficient training time and model capacity. In the second, we changed the number of layers. We added the third hidden layer. Adding one more hidden layer brought accuracy up to 63%. More layers given the model more depth to learn from, but 4 epochs was still not enough to fully train it. For the third, we changed the hidden units, 15 units per hidden layer. Simply giving the model more time to train, 20 epochs instead of 4, brought accuracy all the way up to 73%, even only with 10 neurons. This shows how important training duration is. And for the last one, we changed the number of epochs, 20 instead of 4, with larger. For the fifth one, we changed batch size to 32 instead of 10. We increased it to 32 with larger batch size. The model trains faster per epoch since there are fewer weight updates, but each update is based on more samples at once. This gave 80% accuracy, higher than the baseline 30%, but lower than more epochs or more neurons. Thank you for watching.